Hello everyone, welcome to the part 2 of Recitation 0D. In this part, we'll introduce concatenation, stacking, padding of the tensor, and some useful mathematical operations like element-wise calculation, reduction, comparison, and some matrix operation. So let's get started. The first thing is concatenation. So what is concatenation? Concatenation mainly takes two arguments as input. The first one is the is a sequence of tensors, and the second one is the dimension that you want to concatenate over these tensors. So there's one restrictions on the shape that all input tensors must either have the same shape except in the concatenating dimension or to be empty. So for the first example, uh, T1 and T2 have the same shape 2 by 3 by 4, and we set the dimension argument to 1, and that means we want to concatenate over this second dimension because this dimension argument starts at 0. So the other two, so other dimensions must be the same and will remain the same. So in this example, you have two 3 by 4 matrix inside each tensor, and because you set the dimension to 1, and that means you are stacking the rows of this part and this part, and you're also stacking the rows of this matrix and this matrix. So this is the final result, and only the second dimension have changed, and you are basically joining these rows together. So for the second example, we are passing 3 tensors to our input, and we have 2 more vectors, T3 and T4. So we set this dimension to 0. And for T1, T2, and T3 vector, their first dimension are different because T1 is T3 only have 1 in its first dimension, but for other 2 dimensions, these 3 vectors are all the same. So we can concatenate over this first dimension, and the result will look like this because it is only joining these like 2 by 2 matrix together into a new matrix. For the second example, this T1, T2, and T4, they have different dimension. They have a different third dimension, but for other dimension like D1 and D2, they are the same. So that means we could concatenate over the third dimension, the last dimension, and since there are 4 plus 4 equals 9 elements in its third dimension. So as you can see here, each row will have 9 elements inside, but the other 2 dimensions will remain the same as 2, 3.
Okay, for the tensor stacking, you can regard this
operation as the combination of unsqueeze and concatenation. So let's say we have two tensors, T1 and T2, and their shape is 3,4. This torch.stack function have two important arguments. The first one is a sequence of tensors, and the second argument is the dimension they want to stack over. So if we want to stack T1 and T2 over dimension 0, its first dimension, then PyTorch will first expand or create a new dimension in this first place, and then it would concatenate over this first dimension. So if you have two tensors in this, so if your input tensor array has two tensor, then this n will be 2. So similarly, if you set this dimension to 1, then your output should be 3, 2, 4, and that's similar for dimension equals 2. Tensor padding is used to add or expand the margin, expand the boundary of each side. So let's say X is the matrix that we want to add the padding, and these four are the values are the padding values of each side. So pad left equals 1 means we want to add one more column to the left of this matrix, and then pad bottom equals 2 means we want to add 2 more rows to the bottom of this matrix. And the mode here is the way of adding these padding values. So if we set the mode to constant and the value to 0, that will let this function know that we want to add the constant value 0 to all its extended boundary. And we need to pass this tensor and then the padding value of each size. But of course, you can pass less value like 2 or 3. For those operations, you might need to go to check the document of PyTorch. For mathematical operations, let's first look at the element-wise operation. We first initialize vectors, tensors like this with initial value 1. And if we add a scalar 10 to our tensor T1, then this addition operation will be applied to all positions inside this tensor. So the result is this. If we do the addition between among the tensors, then the corresponding positions will be added together. So the element with index 0 in T1 will be added to the element with index 0 in T2, so on and so forth. So the result will be this. When we multiply our tensor with a scalar, then this multiplication operation will also be applied to all the positions inside this tensor. The multiplication with tensor is basically the same as the addition with tensor. Next, let's look at the broadcasting of element-wise operation. So this T3 and T5 have different shapes. The shape of T3 is 3, 4. The shape of T5 is 3, 1. But PyTorch will automatically help you to broadcast if PyTorch could recognize the broadcastable dimension. So if you add T3 with T5, then this T5 will be first broadcasted to a two-dimensional matrix of shape 3, 4, like T3, and then will be added together. So this element-wise operation will give us a result this. For the reduction operations, you can use it to get some simple statistics of your tensor, like the mean value, the sum, the max value, the mean, or the argmax value. So let's use sum as an example. So to calculate the summation of this tensor, you can either call it tensor.sum or torch.sum and pass this tensor inside. So if you run this t1.sum, then it will sum over all the values inside this t1 tensor and give you the output 3. If you run the sum over this t2 two-dimensional matrix, then you will also sum over the rows and columns and give you the output 12. So for these two examples, you are specifying the axis or the dimension that you want to reduce over. So please look at the PyTorch documentation for these two operations. For the comparison operation, let's first introduce the basic comparison. So this T1 and T2 are two matrices, and if you compare them directly without adding any other operations, then it would compare the same. It will compare the values of the same position. So it will first set the comparison between these first elements into the result here, and then compare the second element of these two and set the result here. So this is the basic comparison. And you can also run this any or all to get the general idea of your result. So any is similar to the logical OR. So if any of your result is true, then it will set the result to true. For this OR operation, if any of this result is false, then the final result will be false. So OR is the same as the logical AND. So if you set this axis or dimension to 0 or 1, that is pretty similar to the sum here. So this is the axis or dimension that you want to reduce over. For the matrix and vector operations, we use the matrix multiplication as an example. And please note that this matrix multiplication is totally different from the pairwise multiplication with the star operator. we introduced before. So this add operator is basically the same as this matrix multiplication function in PyTorch. So if you run this matrix multiplication, then PyTorch will multiply these two tensors following the linear algebra way. So if you are not familiar with linear algebra, please go to check how to do the matrix multiplication and review the knowledge. And we also provided several examples of tensor of multiplication between vectors and vector, matrix and vector, and these tensors with more complex shapes. So you could download this notebook and run these operations by yourself. We also provide this cheat sheet for your reference. And please don't forget to check the PyTorch documentation if you have any questions to the operations that we introduced or you're going to use. So that's all. Thank you.